Hello, welcome everyone. Today we will be discussing comprehensive accelerator data flow co-design optimization for convolutional neural networks. This work is collaboration between University of Utah, Washington State University, and The Ohio State University. Let's look at the motivation for our work. Deep neural networks are finding more applications and they are getting bigger. Convolutional layers are the most compute-intensive operations in most deep neural network pipelines. Optimizing CNNs for fixed architecture is challenging. Significant work has been done on optimizing CNNs on different types of processors like CPUs, GPUs, and even emerging accelerators. Accelerator community uses the term data flow to signify the execution order of a computation. For dense computation, data flow can be represented using loop permutation and loop tiling. Two accelerators with the same number of storage and computational resources can have different data flows, resulting in better performance and better energy efficiency. Similar to optimizing a program on a fixed processor, we consider a more general problem of optimizing both the data flow and the architectural parameters for hardware accelerators within specified constraints such as chip area. Designing accelerator involves set of choosing set of SRAM banks, SRAM capacities, and number of registers per processor element or PE and number of PEs. We propose a solution to this problem. Our approach takes as input 1. Problem specification. These are CNN layer parameters like dilation or strides and sizes of tensors involved in the CNN computation like height, width, and number of channels of input and output activation tensors. 2. Technology parameters. Area of primitive components like SRAM cell area of FP32 multiplier, add unit, etc. Technology parameters also include energy per operation of primitive components. For example, energy required to do single load or store operation at a given level in memory hierarchy, or energy required to do a MAC operation. 3. Optimization criteria. Whether we would like to find architectural parameters and corresponding data flow to reduce the energy or increase the throughput of the CNN operation. These inputs are used to compute A. Symbolic costs, for example, total energy needed for convolution or total delay for that operation. B. Constraints like the array slice at different levels in memory hierarchy aren't bigger than the storage capacity at that level, or the total area of all components shouldn't exceed provided maximum area. We solve the generated nonlinear optimization problem to obtain both architectural parameters and corresponding optimized data flow suited for those architectural parameters. Let us consider the simple example of matrix multiplication. For architecture, let us consider a three-level memory hierarchy. The outermost loops with Di, Dj, Dk iterators traverse on large tiles in DRAM. At every iteration, a tile is brought into SRAM, typically a faster and smaller memory, and accessed multiple times by inner loops. We can permute these loops. Also, we can choose different values for tile sizes at various levels. Choosing different permutations and different values for tile size variables leads to significantly different performance. The PE array collectively accesses tiles in SRAM, and the network on chip does the distribution among PEs. Some loops in the nested loops are marked as for all, denoting these loops are executed in parallel by a set of processors, also known as spatial loops. Permutations of spatial loops have no significance, but the tile size selection of parallel loops do determine utilization of parallel computing resources. All other loops are executed in sequence, also called as temporal loops. These loop permutations and tiling variable choices constitutes different possible data flows for a given accelerator. As we saw before, matrix multiplication has 3 nested loops. CNN, however, has 7 nested loops. With n-level memory hierarchy, for CNN, we have 7 factorial raised to n number of permutations and 7 into n minus 2 tiling variables to choose values for. The search space for finding optimal permutation and tile sizes or a data flow, even for a fixed architecture, is huge. In addition to that challenge, if we were given maximum accelerator area and we need to choose architectural parameters like number of registers per PE, number of PEs, and size of SRAM, the search space gets even larger. Also, the optimal data flow differs for each choice of architectural parameter. In order to co-design data flow and architecture for a given area budget and set of representative workloads, we use this overall methodology. We start with each CNN layer in the workload. We do loop permutation pruning to consider subset of all loop permutations which are more promising. We compute symbolic data footprint and data volume expressions at each memory level in the memory hierarchy for each selected candidate. We use these expressions to auto-generate nonlinear optimization problem. We solve this optimization problem using CVX-PI solver. We propose formulating constraint optimization problem to solve this problem involving humongous search space. This slide shows formulation for minimizing energy. Energy at each level in memory hierarchy can be found by multiplying access cost per operation at the memory level and total number of accesses at that level. The next constraint, make sure that the footprint of all arrays at a level is smaller than the capacity at that level. In other words, it makes sure that we don't use unrealistic tile sizes that would cause the array slices to not fit in the scratch pad. The last constraint, make sure that we stay under the budget for area. The access cost at level is dependent on memory technology used at that level. For example, registers, SRAM, or DRAM, and storage capacity at that level. We can use Accelergy from Neely Wu et al. To find this metric. Accelergy in turn inquires Aladdin or Cacti or vendor-specific databases for this info and extrapolates if needed. The formulation for minimizing delay is similar to earlier formulation, except instead of summation, we use maximum delay across storage hierarchy. The storage level causing highest delay is the bottleneck level in the computation. This slide shows an example of auto-generated optimization problem formulation. The audience is not required to understand all of the details in this formulation, We are just showing this as an example. This set of constraints define problem sizes. In this case, we are dealing with output tensor of size 112 by 112 in height and width and 64 channels. The weight tensor is of size 7 by 7. This expression shows total energy expression as a summation of energies at register, SRAM, and DRAM level. This section shows data volume expressions generated for number of SRAM and DRAM accesses. These set of constraints describe capacity constraints. These constraints use data footprint expressions. Both the data footprint and data volume expressions are functions of tile size variables. The capacities at different levels in memory hierarchy, R capacity, S capacity, etc., are also variables in optimization problem in addition to tile sizes. Let us define a couple of terminologies. Data footprint is slice of array stored at a given memory level. Data volume is the total number of accesses to the array slice stored at that memory level. For example, consider the outer product of two arrays A and B. The code illustrates the computation. The footprint of array A is n. That is the total size of array slice. But the data volume or number of accesses to A are n squared. Now consider data footprint for array B. It's n. And the data volume for B is also n. This is because the inner loop can reuse the cached load in variable reg instead of accessing it from array slice repeatedly. Note, permutating the loops in this example and caching the element of A instead of B will cause volumes of A and B to be n and n squared respectively. Now that we have seen the definition of data footprint and data volume, let's look at a procedure to compute these quantities at a given level in memory hierarchy. The inputs to the procedure are data footprint expressions at the lower level in the memory hierarchy and the loop permutation from innermost loop to the outermost loop at the given level. The input tensor is indexed using iterators N, C, H, W, R, S. The output tensor is accessed using iterators N, K, H, and W. Initially, we set data volume at this level same as the data footprint at lower level. This denotes the least amount of accesses that would happen while transferring the slice from this level to the lower level. We update data volume of an array by replacing old symbolic trip count RR by new symbolic trip count QR times RR for the first time. The resultant expression is manifestation of partial reuse caused by the sliding window as shown. If the iterator isn't used in the index expression of an array, we keep the footprint intact. The unchanged expression denotes full reuse at the loop level. This is the case for the output tensor. The next set of iterators we see in the loop permutation are S and C. Neither of these iterator occur in the index expression for the output array. So we keep that expression intact. We still get reuse for the output slice. These iterators, however, do appear in the index expression for the input tensor. This time, we multiply the trip counts to the volume expression, observing that no additional reuse is possible for the input slice. The next loop we see is the H loop. Iterator H is used in index expression for output tensor. We replace RH by QH RH. Incidentally, for output tensor, there is no possibility of partial reuse, and henceforth, we will stop getting reuse for output slice. This slide denotes the final data volume expressions considering all loops at this tiling level for input tensor and output tensor. The computation of data volume for weight tensor is similar to that of output tensor. We omit computation of footprints for brevity. Let us discuss some key results. Accelerator architects need to make resource allocation choices to distribute the area budget among different components. Our framework can help architects with that decision making. This graph denotes energy spent per MAC operation for executing CNN layers from ResNet 18 and YOLO 9000. We choose Iris resource allocation as an example of fixed resource allocation. We choose Iris resource allocation due to its availability in the modeling software. Co-designing architectural parameters and corresponding data flow using our strategy can lead to significant reduction in energy usage. We use the best data flow for architectural parameters of Iris. We use the same budget of Iris to choose architectural parameters and corresponding data flow. The green line shows choosing separate architectural parameters for every CNN layer. It is not, however, practical. So we choose single architecture corresponding to the dominant layer in the whole dataset amongst all layers of ResNet 18 and YOLO 9000. Using that architecture, we do data flow optimization for all other layers. The resultant energy trend is shown as the orange line. This slide shows similar exploration for delay optimization. Optimizing for every layer is better than optimizing for dominant layer, but even optimizing considering the dominant layer is better than fixed architecture allocation. We present a novel solution to data flow optimization problem for CNN accelerators by formulating and solving a constrained nonlinear, in particular discipline geometric programming optimization problem that is solved by off-the-shelf convex solver CVXPy. A novel solution to architecture data flow co-design problem for CNN accelerators optimizing across parameters for per PE register capacity, SRAM capacity, and number of P's, avoiding the need to solve data flow optimization problems for various combinations of choices for architectural parameters. We present experimental results using state-of-art accelerator modeling framework, time loop, showing that significant improvement to energy efficiency and performance over prior designs are achieved by use of developed design space exploration methodology. We thank you for attending our talk. We thank authors of all prior works, CGO organizers, and reviewers. We also thank NSF for funding and CHPC for resources and support.